Here we have a comparison test for improper integrals. Sometimes it is impossible to find the exact value of an improper integral, and yet it is important to know whether it is convergent or divergent. In such cases, the following theorem is useful. Although we state it for type 1 integrals, a similar theorem is true for type 2 integrals. So the comparison theorem. So suppose we have functions f and g and are continuous functions, with f of x being greater than or equal to g of x, which is greater than or equal to 0, for x is greater than or equal to a. So part A, if we have a function and we're taking the integral from a lower limit of a to an upper limit of infinity is convergent, then the limit, the integral from a to infinity of g of x dx is convergent. Part B, if we have that function taking the integral from a to infinity of g of x dx is divergent, then we can say that the function f of x dx going from a to infinity is divergent. Now, we omit the proof of the comparison theorem, but in figure 12 makes it seem plausible. So if the area under the top curve, f of x, is finite, so they're saying everything underneath here is finite, then so is the area under the bottom curve, which is g of x. And if the area under the curve of g of x is infinite, then we can say that the area is also infinite under f of x. Note that the reverse is not necessarily true. So if we're saying that the g of x, taking the integral of g of x, is convergent, f of x may or may not be convergent. And if we're saying that f of x is divergent, then g of x may or may not be divergent.